This is the Automated Buffing Machine by GVSU Senior Project Team Number 4, sponsored by AutoCam Medical. The sponsor contact throughout this project was Mitchell Mayberry, the GVSU project advisor was Dr. Christopher Pung, and team members included Connor Whaley, Kaz Stewart, Mark Feldposh, Matthew O'Brien, and Nick Hahn.
The purpose of the Automated Buffing Machine project is to automate one of the steps in the production of one of the medical-grade drill bits produced by the sponsor, AutoCam Medical. This is a 2.5 diameter bit, available in two lengths. The project focuses on the longer variation. In this step of the process, the portion of the bit which interfaces with the drill driver is polished in order to remove titanium nitride overspray from the previous operation, as well as obtain a pleasing surface finish. The parts of the bit which are to be buffed are the AO diameter, the chamfer feature, and the end of the bit.
The agreed-upon project specifications, which are detailed in the project scoping document as well as in the final project report, consist of the following. The machine must run on 120-volt AC power and 80 psi air supplied from the Vention shop. The cycle time must be no more than 40 seconds to be verified with a stopwatch during the final testing. The machine must be able to accommodate 500 parts per run. The bits which the machine must be able to buff are contained under AutoCam part number 100902 and are 2.5 mm in diameter. The robot system used must be a Universal Robots 5E. All safety equipment must be verified for correct functionality. Safety equipment for this machine consists of Lexan panels around the machine, an interlock for the maintenance doors on the back of the machine, a light curtain guarding the open front face of the machine, and an easily accessible emergency stop button. The machine must pick drill bits from a pallet, as supplied by the sponsor, with no special intervention required to prepare the pallet of bits. The machine must also place the buffed bits into another identical pallet in a similar orientation. For the purpose of the testing, an acceptable buff condition must consist of DICOM being fully removed from the surface of the bit's AO connector. A minimum of 95% of parts must pass the final test. Paint or other cosmetic considerations are not specified for the machine. And most critically, the machine must not remove more than 2/10,000ths of an inch of material from the AO diameter of the bits, thus informing the criteria for passed versus failed bits in the final test.
As shown here, the automated buffing process consists of numerous steps. At the beginning of a run, the robot will grab one bit from the incoming pallet and load it into the air chuck. The two linear axes, as well as the rotational axis, slowly move to their respective home positions in order to establish where zero is in their individual coordinate systems. This is especially crucial in the case of power loss during a run, as the program will not retain information about where the axes are located relative to their home positions. The homing process also includes extra rotational movement in the rotational axis for internal lubrication purposes. The rest of the run consists of the following steps being repeated until all bits are finished. A cycle starts with a bit already loaded into the incoming gripper, as this is the state of the machine after homing is complete. This bit is loaded into the air chuck, and then the robot moves to retrieve the next bit from an incoming pallet. While this is happening, the buffing operation begins. First, the buffing wheel advances towards the air chuck and buffs the end of the bit. Every run, the location where the end of the bit contacts the wheel is incremented across a 20 millimeter wide band in order to avoid creating a groove in the wheel, which would negatively impact the chamfer feature. Next, the X and Y axis move in order to buff the AO diameter of the bit against the face of the buffing wheel. This is done in 3 stages to ensure that the entire AO diameter is buffed. Finally, the buffing wheel rotates by 45 degrees in order to buff the chamfer feature. This is also incremented in order to avoid creating a groove in the buffing wheel. Upon completion of this step, the robot swoops in and removes the finished bit from the air chuck using its second outgoing gripper. The following incoming bit, which the robot grabbed while the buffing operation was taking place, is immediately inserted into the air chuck to reduce cycle time. As the buffing operation begins again on the new bit, the previously buffed bit is placed into an outgoing pallet and the robot again retrieves the next incoming bit.
Small tests were conducted throughout the project, generally of about 20 bits, in order to verify proper operation of the various components of the process. Initial tests involved hand feeding bits into the air chuck in order to verify and fine-tune the buffing operation. Specific variables that were adjusted included timing, air pressure to the pressure tables, and servo speeds. Concurrent to this testing, general process for the robot's movements was tested in order to finalize the end of arm tool design, specifically with regards to gripper placement and gripper finger design. Upon verification of the buffing process and completion of the end of arm tool design, programming and testing of the full operation could begin. This began with palletization programming until the robot could reliably pick and place bits. Next, this process was expanded to placing bits into and removing them from the air chuck. Finally, the full process could be tested.
The full process was tested with 2 runoff studies. The first consisted of a 500-part run. These 500 parts were bits which had already been finished by an operator by hand, and thus they no longer had the critical titanium nitride overspray. During this test and all prior tests, this overspray was accurately simulated using red Dicam layout fluid, carefully applied to the bits. This coating buffs off similarly to titanium nitride overspray. This 500-part run was designed to require zero intervention, as it should simulate a normal production run of bits. The diameter of the bits was measured using micrometers in 3 places along the AO diameter. Measurements were performed prior to Dicam application, after Dicam application, and after buffing. The pre-Dicam and post-buffing measurements were compared to evaluate if a bit passed.
The second runoff study consisted of buffing 100 bits without any Dicam applied in order to evaluate surface condition.
Overall, our project was very successful. We met our cycle time requirement with an average cycle time of 38 seconds, and were easily able to meet the 95% pass rate requirement. We were able to verify these requirements by performing a 500-piece runoff study. Additionally, we were able to successfully integrate all of the sponsor-mandated equipment and safety features.
Throughout the project, numerous challenges were encountered and overcome. These ranged from supplier issues starting early on in the project to the many hours spent fine-tuning end-of-arm tool movements in order to reliably get the bits where they need to be on time. A large portion of the machine utilizes components, both mechanical and controls, from Vention, who specialize in modular control solutions. Unfortunately, this is where all of our supplier issues occurred. To name a few, we encountered a major software issue that did not allow us to control multiple servos simultaneously at different speeds. We found that their mechanical and electrical diagrams and instructions were extremely poor. We had one of our I/O modules fail due to a faulty component, and common with all of these issues and more was an overall challenging customer service experience, which required extensive follow-up work on the behalf of the team, at times extending for months. Despite this experience, we were always able to find solutions to all of the resulting issues, which often involved cutting out the Vention equipment entirely and seeking other solutions. As an example, the turnaround time for repair of our I/O modules was longer than we had been promised, and thus we chose to eliminate both modules and control any necessary I/O pins directly from the Universal Robots control box. Most of the rest of the issues that we encountered came from fine-tuning the various operations involved in the automated buffing process. This was split into 2 main categories. The first that we worked on was the buffing operation, and the second was the robotic movements. Regarding the buffing operation, overcoming the challenges here included extensive testing and adjustments to the process, including varying air pressure to the pneumatic pressure tables, varying the duration of buffing on specific parts of the bit, such as the AO diameter or the chamfer, in order to achieve the correct surface condition while not exceeding the material removal limit, varying the location at which the bit was buffed against the wheel in order to minimize buffing wheel wear, and especially investigating ways to speed up the process in order to meet our cycle time requirement. This was especially challenging due to the limitations placed on the adjustability of our servo speeds due to the previously mentioned Vention software issue. Regarding the robotic movements, challenges included accurately feeding the 2.5mm drill bit into the 1/8 inch or 3.1mm collet, accurately picking bits from and dropping bits off in the pallets, and pallet placement, which itself broke down into issues of ensuring easily repeatable and accurate pallet placement by the operators at the beginning of a run, as well as ensuring the end-of-arm tooling on the robot could reach all 1200 bit locations on the pallets without interfering with bits that may be in adjacent pallets, which was especially difficult due to the space constraints on our machine.